After recording this presentation 3 times, because first I just misspoke so many times, I couldn't stand it. Usually I'm not that fussy because I try to ad-lib these. But then the second and third recordings were just ruined by background noise. And we have Windows 11 and Microsoft to thank for that. God, I wish I hadn't upgraded. But we're going to talk about the third rail of the Collatz conjecture. And I'm serious, there is a third rail. And it will result in a proof of the Collatz conjecture. And this is the third rail. It's an operation. It's n minus 1 multiplied by a quarter, which is the same as n minus 1 divided by 4, or n minus 1 multiplied by 0.25, whichever you prefer. And I call this the hidden operation C, such that n is an odd number. N is an odd number, always. Because I only study odd numbers in Collatz sequences, I am not in the least bit interested in even numbers. So why is this operation hidden? Well, I'll just briefly say here that it involves a set of superset numbers. It is a superset number. It's one of the 2 types of superset numbers, and they're only apparent in odd-only sequences. The other is that the convergence of sequences is mediated by this number. There's always one case of this superset number, and in every merge, and that is not evident when you study the even sequences. In fact, it's completely obliterated or hidden or obfuscated by the even numbers. So that's why any mathematician who's foolish enough to study the even numbers is going to miss this altogether. And even those who use the odd-only function, which is the Syracuse function, which is really hard for someone like me to nail down what's happening there, but they're eliminating the exponents of 2, I have a feeling they're not going to see this either. Now, why does it matter? Because this is really important. Every odd number is a member of a convergent sequence, no matter what the 3x plus 1 function says. That certain numbers are not part of every sequence is actually an artifact of the 3x plus 1 function. If you can prove it's true for a superset function, then it's also going to be true for the subset function, which is 3x plus 1. And if you can prove that every odd number converges on a if every sequence is convergent on an odd number, there can be no infinitely divergent sequences. There cannot be no infinitely divergent sequences because all the odd numbers are taken. There's one little thing that I've forgotten the name of it. I think it's called the pigeonhole principle. This is like the ultimate case of the pigeonhole principle, because every odd number is already accounted for by a sequence, or every sequence is already accounted for by an odd number. Here we have a graphing of the odd numbers. For what it's worth, I think this is part of 27, a segment of 27. And if we click on these first 3, we see a steep ascent, and that's because they're operation A. And operation A is n plus 1 times 1.5 minus 1. And so remind yourself that n is a minus number. No, it's not a minus number. It's an odd number. Plus 1 makes an even number. Then you're able to multiply it by 1.5 without creating a decimal place or a fraction. And I hope you know that in number theory, whole numbers is the whole game. Everything in number theory really is about whole numbers unless you go into complex analysis. So let's see if I can think of one offhand. I probably can't. I'm not very good at that, but say it was 7, plus 1 would be 8, times 1.5 would be 12, and then minus 1 would be 11. So that's operation A. You've gone from 7 to 11, and that's approximately 1.5 if you don't do the addition by 1 and subtraction by 1. Then we take a steep ascent, using C, which is m minus 1 times a quarter. And this takes us all the way down here. So it's like a game of snakes and ladders, or chutes and ladders, whatever they call it in the US, chutes and ladders, I think, which is just wiped out 3 operation A's. And then you come to a series of shallow descents, slopes called B. They're B because they're times 0.75, so they're also a reducing operation, just not as extreme as 0.25. So you get the idea that there are 3 operations acting on sequences. Oh, I just added some more things, I think, didn't I? So here we have a slide, a busy slide about the equivalence of even, odd, and ordinary functions. And again, we note there's operation A, B, and C. And we notice that in the first case, A, there's 1 division by A. There's 1 division by 2 in the even-odd version. And the odd version, my version, is never going to have an even number. Obviously, it's just direct from 11 to 17. In operation B, we have 2 divisions by 2. And again, my version is just a direct odd sequence, 17 to 13, whereas 2 even numbers have been inserted in the even odd version. And the third one, C, is a little bit different because you can have 3 divisions by 2 in the even odd version, or you can even have more than that. And in fact, you can have many more than that if it's a power of 2, a large power of 2, because they end in 1. But with each division by 3, and here's a case 29 to 11, we have the situation where in my version we need an intermediate number, and that intermediate number is 29 minus 1 divided by 4, so it's a third rail number, and that's completely invisible in the even-odd sequences because it's obscured by 3 divisions of 2 or more than that. And then mine continues on to the same odd number as the even-odd operation ends with, or doesn't end with, but gets to. And I'm trying to think of a succinct way to explain that, but I'm not sure it's worth it, because as you see, it returns to 11. So there are no numbers in the even-odd sequence that are not in the odd sequence. So, but the odd sequence has some extra odd numbers, so it's considered a superset sequence, a proper superset sequence. It not only has these extra odd numbers, but it has all the odd numbers from the even-odd sequence. Moving along. Oh, I've got some animation that will do. And we'll look at those very briefly in the next slide, I think. Oh, no. Okay, I've got to go back to this. So there are 3 disjoint series that can be defined for all of n, the natural numbers, the infinite set of the natural numbers. And n plus 1 is evenly divisible by 4. And that produces a series of numbers 3, 7, 11, 15, 19, 23, 27, 31, 35. And those, the thing about this one is that there are twice as many numbers in this series as the other series because they're 4 apart. And curiously enough, when mathematicians think about infinity, they will say each of these series is infinite. The other series are 8 apart, both of them. And still, each series is essentially an infinite series. So you cannot say the first series is longer or bigger. It has the same cardinality as the other series. So n minus 1, so we've added 1 to n in the first case. And remember, n is always odd. So what we're doing is making it even so we can perform an operation on it. A congruence operation. These are congruence operations, divisibility by 4, 8, and 4 again. So n minus 1 is evenly divisible by 8, and then so that's 1, 9, 17, 25, 33, 8 apart, and n minus 1 is evenly divisible by 4. That's 5, 13, 21, 29, 37. Again, 8 apart. And if you're wondering why 1 is under congruence B, that's simply because 1 minus 1 is 0. Once that happens, the divisibility question is moot. It cannot be 8. It cannot be A because 1 plus 1 is 2. That's certainly not evenly divisible by 4. And it's not 1 minus 1 because here, well, let's put it this way. It's already taken. It's already been taken by B. And you have to take these in order. So C can't take it. Or C. That's the third rail. Let's move on. Now that's strange. Hope I haven't skipped a slide. This is a first recurrence table. Anyway, that's what I'm calling it. And this idea was developed by a French mathematician about a century or more ago. And that means it was called a Poincaré map. That was his name. And he realized a lot of dynamical systems can be simplified. And he said, observe the point at which a periodic orbit returns to the first value. And yeah, Collatz sequences are often termed orbits, which is a bit pretentious. Then create a map table, their equivalent, to send the first point to the second, hence the name first recurrence map. Now, I believe this does apply to what I'm doing because I'm eliminating the recursive part of the partial functions or operations. So in the function, I've got m plus 1 times 1.5 minus 1. So that's that. I've added 1 to n, multiplied it by 1.5, and then subtracted 1. That gives a whole number if m plus 1 is congruent 0 mod 4. That's the input n. Similarly, I have 1 here for 0.75 and the third rail. And again, you notice that you only add plus 1 to the first one because that's the only way to get a, am I saying this right? I don't want to make a mistake, or I won't say anything. Just remember that you take these operations in order when using this function. And then, there you go, m minus 1 times a quarter. And so you can think of this column as the third rail. And that's operation C. And look what happened to the numbers on the third rail. Each one has an output that's a consecutive odd integer, 1, 3, 5, 7, 9, 10, 11, 13, 15. Just from the numbers in the third column, which are 8 apart. Well, what are we to make of that? Well, apart from the arithmetic of it, because remember we're dividing by 8, we have a means to show that every odd number is the output of a converging sequence. How else could it be? If every odd number has is an output of a convergent sequence, we have basically solved, or we have huge, insurmountable amount of evidence that there could be divergent sequences, or there cannot be divergent sequences, because every convergent sequence is taken, or every odd number is taken. That's a really strong argument. That's inductive reasoning, informal inductive reasoning. It wouldn't be enough to collect that $1 million prize in Japan, but I'm sure a mathematician could run with this. So this is what you see with an even-odd sequence. You see each of these numbers on the left, and put the laser pointer on, maybe it helps a little bit. It won't go on now. Unbelievable. Let's try one last time. No. So 109, 117, 125, 133, and 141, those are operation C numbers. They're congruence C, and the output is operation C. And look what happens. They hit, or they generate 3 even numbers, or 5 even numbers, or 4 even numbers. And then they arrive at another number which the congruence of which, and they don't even think about congruence as far as I know. It's indeterminate. It's not B or C. Well, depends how you look at it. But it's indeterminate. It's indeterminate that 109 goes to 41 and 117 goes to 11. This just makes no sense. That's why my function is just so great. So this is what you see with the odd-only sequences using my function. You see one intermediate odd number, except for one of those. So 109 minus 1 divided by 4 is 27, 117 minus 1 divided by 4 is 29, 110 is 25 minus 1 divided by 4 is 31, and so on. And in the case of 117, where we see these additional divisions by 2, so obviously we're going to a very small number, we do get this intermediate odd number of 11, and then we go to 7, and then we go to 11. Now, I said that the 11 is indeterminate, what its relationship is to 117, and I mean that. I don't think you'll get a whole number out of this, whatever you do. But mine, the 11, the 7 has this C relationship to 29, and the 11 has this A relationship to 7. So my sequence makes much more sense than the even-odd sequence. Anything else? Yeah, so there's a C operations. Let's say minus 1 times a quarter. And now our next slide. So here we have even-odd and odd-only graphing of a small number, 117. It's not particularly small. It just has a few limited number of steps. I wonder if I can put my picture over while I'm recording. No. So these sequences are the same, but operation C is hidden in the even-odd sequence by multiple divisions of 2. So you will see that 29, I'll try the laser pointer again. No? Yeah, there. 29 is not present in the even-odd sequence. It's just missing. And the reason it's missing is because we got all these even numbers here. We're out of control with even numbers. 1, 2, 3, 4, 5. So it slips in. So the odd one, my one, slips in 29 and 7. And I think we had that on the previous slide. And then it goes to 11 straight away, whereas 11 here is down here. And you will see that even though the even-odd sequence is much longer, apparently, than the odd sequence, the odd-only sequence. There are, in fact, more odd numbers in the odd-only sequence than the even-odd sequence. So this has got properties that it's a smaller set. It's a much smaller set of odd numbers than even odd numbers, and even within those odd numbers, there are these superset numbers. So it's just much more concise. You see here in the even odd one, you've got tons of divisions by 2, tons of them. And you're only left with a few odd numbers: 11, 17, 13, 5, and 1. So I think it's pretty sad that mathematicians still study the even odd numbers. It's so pointless, and it shows that they're missing the obvious thing, that there's this arithmetic relationship between the odd numbers, and there's only 3 of them: 1.5, 0.75, and 0.25. Okay. Oh, so yeah, I'm just filling those in. Every odd number has 2 inputs, meaning it is the next step of 2 convergent sequences. This is the whole story. As I mentioned before, one of those is always C. So we see 2 ways to get to 11. One is with 7, and one is with 45. So 45 is the C operation. Hold on, I'm hoping to get some letters here. Yeah, so 45 is the C operation, and the other operation for 11 is 7. And so obviously there's only one 11 in the output. So it's just an artifact of the table that you see 2, but it's useful. Then the other one is 9 here, and that's a B congruence, and again a C congruence. Every single integer has a convergence of 2 operations. One is an A or B operation, and one is a C operation. So this is the beauty part of it. And then the even odd sequences converge on the subsequent odd number. As we've kind of explained, and I don't want to get confused by these sequences, so I won't even bother, but you'll see, again, they're convergent. You have 2 operations converging. One of those does correspond with C if you start the sequence on C. If you don't start the sequence on C, you won't see it. Again, 7 and 45, if you don't start the sequence on 45, you will not see it in the sequence. So that is clearly a deficiency of the 3x plus 1 function. That's what makes it a subset function. It's not good for the whole set of the natural numbers. In fact, a huge chunk of the natural numbers is missing. I tried once to figure out if I could do it in percentage, but that's just a deficiency in my math theorem knowledge. No, you can't, because all these sets, as I just previously mentioned, these subsets have the same cardinality, so you can't compare them that way. Which is good for me, because that strengthens the reason for a superset function. So this is the next to last slide, I think. So when we sort output, we see that all integers except for multiples of 3 have 2 inputs, and we can exclude from consideration the odd numbers evenly divisible by 3, as they occur only as the first number in even-odd sequences, for example 27. Again, there is a number before 27, it's 109, and when you use the conventional sequence, it skips 109, it skips 27, I think it goes straight to 41. And that's why, again, and that's a third rail, let's just say that. 109 to 27 is a third rail. In this table, we actually have 2 tables. On the left 2 columns, we have the input of the consecutive odd numbers, and in the output we have, and that's has a recurring cycle of 4 in terms of congruence, BACA, BACA. In the output column, we get this little jumble, but we know it's not a jumble from the previous slide. And this has a 16 unit cycle, and then it repeats itself. Believe me, it really does repeat itself. Every 16 units, the congruence cycle repeats. Now, what's really nice about this is that if you sort by output in the right side, you then get this organization of BB, A, CC, AA, B, AA, CC. So what's going on here is we can see that the multiples of 3, or the numbers evenly divisible by 3, are only convergent with one letter, A or B or C. And again, I think, let's skip that reason. So we see here that 1 and 5 converge on 1 and 1. So we have this little conceit that 1 is converging on 1, and that's fine. There's nothing wrong with that, and that's really the case in the even odd numbers. As we know, there's a trivial loop, 1, 4, 2, 1. And this is the basis case, 1 to 1 and 5 to 1. That is the basis case for every following pair of sequences. That is essentially an inductive proof. So we have 3 to 5 and 21 to 5, and that's C, and then we have 9 to 7 and 29 to 7, and that's A, obviously because these numbers are the same. Why am I even saying this? There's 1, 1, there's 1, 5, there's 1, 7, and so on. 1, 11, 1, 13. But there's two numbers, two outputs, or two inputs, excuse me, for each of these, two inputs, as we already showed. So the inputs for 13 are 17 and 53. The inputs for 17 are 11 and 69. And in each case, one of those inputs is C. Now, I think we have got to, oh, I've just got a little animation here. We've got to the end. And so what I've been saying all along, I'm going to say one more time, because you got to say what you said. Every odd number is the output of two sequences. Beginning with 1, we see the basis case of 5 congruent C goes to 1, and 1 goes to 1. So that's two converging sequences. And then every sequence must extend this convergence without exception through the infinite ascent of a number line. Because this property holds for all odd integers. There cannot be an exception to this. There really can't. It's just arithmetic. It's congruence. Since every integer belongs to a convergent sequence, which is C, the third rail, ipso facto, there can be no infinitely divergent sequence. Say it one more time. Since every integer belongs to a convergent sequence, ipso facto, there can be no infinitely divergent sequence. Thank you very much. See you next time.